Hello and welcome everyone. We are excited to have you with us today for this webinar. So, this is Jeevan with FTD Infocom, and I truly appreciate you taking your valuable time in joining for this webinar, whether you are joining from office or home or on the go. Thank you for joining. So, for people for people who don't know about FTD Infocom, FTD Infocom hired from Future Techno Design in the year 2008, and we have a experience of more than 2 decades. We are pioneering innovation in engineering, VLSI, and digital transformation. And FTD is India's first company who are focused on VLSI software domain. We have over 10 patent silicon IPs, and we pioneer in MEMS technology in India. We are headquartered in Bangalore, and the other offices in India include Hyderabad, Delhi, and also in Singapore. We are global partners, partnered with Siemens, Cadence, Intel, NEC Japan, and ARM. We help set up offshore development centers for Avanti, Toshiba, Creative Multimedia, Elpida, Topan, etc. And FTD, we are partnered with 25 plus global software principals. One of the proud achievement by FTD is the LEOS inclinometer, which is like we have supported LEOS for ISRO for 14 years for their MEMS development. We developed inclinometer, which is using the MEMS software tool, micro electromechanical systems. Using our support, they have operated MEMS device in the lunar environment. Talking about the market reach and customer base of FTD, we serve almost like 2000 plus customers across India. That includes the defense, government labs, medical, consumer electronics, and all the automotive and aerospace customers. By looking into the slide, you can understand the number of customers that we serve. And that's it from my end. I hand it over to Mr. Shivakumar, who is our speaker for the day. Thank you all.
Good to go? Okay. All right. Just reconfirming. Thank you, Jeevan, for that very quick but very effective introduction about what FTD does. Good afternoon, everyone. Thank you for joining in again. We have had some interactions with you in the past, some of you. My name is Shiv Kumar. You can call me Shiva. I'm an independent consultant working as a collaborator with FTD Infocom now. The objective of this webinar is essentially to walk you through the space systems thermal. What we will do today is we'll walk you through a couple of insights on space systems thermal, primarily in and around the workflows, as we mentioned, the first one. And the second one that we look at is how can you bottle or how can you capture the inputs of your day-to-day workflows and see the possibility of automation. Third one is we'll keep referring to some cross references of the customer successes, be it NASA, GPL, be it ISRO, or some of the private players. So with that, let's quickly get started. What you will see is a very short video of reusable rocket launchers. At the same time, we are also talking about the moon landers. For example, what you see on the screen. As Jeevan did mention that FTD partners with Siemens to bring Siemens's premium portfolios to the customers like you, which includes Space Systems Thermal. And in the previous slide, we also saw the NASA's LRO mission, where we had the thermal profile available for the south pole of moon, the temperature profile that was available now that can be accessed and that can be modeled using SimCenter, Space Systems Thermal. Moving on, the agenda for today, as we have published earlier in the invite that you might have used to register, is we will look at the next generation thermal simulation tools from Siemens, essentially unifying the conductive, radiative, as well as say the orbital loads in a single platform or the unified platform. Then we'll do a quick hands-on workflow where we will talk about how leveraging a CAD example to start with, doing an analysis of SJK satellite, and then we will very quickly see how that translates from the CAD environment to the simulation, in this case, the space systems thermal, and then it gets on to the downstream workflows like kinematics, which can be done on a concurrent basis. Then, as I did mention earlier, we will take a very quick look at the real mission stories, how this is as a software and as a consultative tool used in tandem with the real mission profiles. So with that, let's get started. The first element of the conversation, which is leveraging CAD. Predominantly, most of you are aware that this forms the fundamental block of your new product development or the references. What we would ideally would like to do is we'd like to have a couple of configurations for a given satellite or a couple of options even before you baseline your design. Even the operational aspects, for example, whether it is the stationary phase or whether it is the deployed phase. What I'm pointing you to is the deployed phase of the antenna on my screen, top right, top left corner of the image. And these are some of the insights that we will drive through the conversation when we will see the subsequent ones. So what you are going to see is, if you are a novice user or possibly the first time entrant to the NXCAD environment, this is the holistic NXCAD environment, or should I say the NX platform, where the applications are aligned based on the deep feature functions that they carry, which represents or which reflects the industry workflows, for example, modeling, assembly, drafting, and so on. So what you see is a SJF assembly, and on the left-hand side, you will see assembly navigator to start with. And what we would like to do is we would like to take a quick look at how are we going to navigate through this assembly, just to do a few checks. For example, the antenna is in the deployed condition. Then we have a couple of sub-assembly elements which we can quickly navigate through. For example, the star tracker, the bus, the boom, and of course, the payload. And if I go a bit more detail into the payloads, and here is a bit more deeper insight for you, where in the payloads, you have PCU, MCU, heater, and pallet units. And this is the area of focus for us, where we would like to do some thermal simulation to start with, essentially to capture the amount of heat that is getting generated through the virtue of radiation and, of course, the conduction. The backside of the payload that you saw, the three perforations or the three slots, virtually represents the cooling mechanism that we will talk about it in a minute. Once you have inspected or navigated through the assembly, the time for us now is to create a simulation. In this case, you would want to start with a assembly FEM. You heard me right? SimCenter 3D helps you to create assembly FEM, just like the way you will create your CAD assemblies, and helps you to map or superimpose the CAD assembly architecture to the simulation, thereby making sure that your CAD and simulation are in sync and helps you to make the local changes very quickly. On the left hand, the top left screen of the simulation navigator, you are able to see now that we are positioning or we are bringing in the part level meshes that we have done, and we are going to assemble them. So this is typically a bottom-up approach of assembling the FEM, where you have a couple of FEM parts, and then you would want to bring them in and assemble uh, to define the complete assembly. In this case, the SJF satellite. So some of the components which are deployed or which are populated with the FEM are annotated in green color, whereas for the rest of them, which are not, still needs to be populated, they are either left gray or some of them are ignored, depending on the choices that you make. Assembly FEM also gives you a provision where you can drill down to a particular sub-assembly or a component, check for quality criteria. For instance, you can check for the materials, you can check for the real-time attributes, and once done, you can reconfirm the entire assembly is being assembled or mapped to your satisfaction. So what you see on the left-hand side is the mesh of the assembly, which is an integration or which is a combination of multiple parts. So this is one approach that SimCenter Space Systems Thermal takes. The next thing that you would want to do is you want to induce a change into the assembly. For example, you would want to see the antenna being stored in the stored condition. Earlier, we had put it in the deployed condition, but suddenly, because of there is a change in the CAD, you also see that the assembly FEM is out of date. Once you hit a quick update button on the top left corner, as you saw, then you see that the mesh of the antenna and the corresponding holders will also get updated. So this gives you a tremendous ability to do a quick check in terms of the changes of the design that you would want to do, and further refine or further take the assembly through the next set of boundary conditions. What we would like to do is I'll quickly walk you through a couple of more workflows with SimCenter 3D Space Systems Thermal. We are going to use a live example here. You can indicate to us in the chat box if we are not able to see the SimCenter 3D screen. Okay. So if you are, as I indicated, if you are the first time user for of SimCenter 3D, this is going to be the user interface that you see. And like you have in your most of the CAD environments, you also see we have a simulation navigator, which essentially helps you to navigate through multiple aspects of your model, including the geometry that you have specified here. And of course, it goes into the simulation, it goes into the FEM file, and so on. Now, what are we looking at here right now is we are looking at the assembly FEM file. If you pay a little closer attention, you see a series of elements which are meshed either in the 3D space or in the 2D space, depending on the modeling approach that you would want to take. What I really want to spend some time explaining to you here today is you have the thermal model available to you, or you have created the mesh through the meshing practices. So these are the simulation environments that we are into. The first thing that I would like to look at is if I have to do a space systems thermal model, we need to set up some initial conditions. The first one being what is the orbit that you would want to model. So space systems thermal gives us the ability to model various planets, including Earth, Venus, Mercury, Saturn. And if you have no specific planet to model, you can start with a generic one, as you would see on the screen. The second that you would like to look at is the orbit, where we are looking at the classical geostationary or the sun synchronous or Mollinia and so on. So this gives you the flexibility of playing around the planet and the orbit type. And you are going to look at depending on the choices that you make, the orbit periods are locked. These are the calculations that are done automatically at the back end. You will be able to look at the orbit period. The second part that you are going to look at is how the orbit is or how the satellite is going to be positioned, hovering the Earth in the classical orbit type. This is where you're going to specify what we call as the vectors, which essentially helps you to position the satellite in the context of sun, as well as say the orbiting entity. Okay. Now, either you can leave it with the current choices, or you can make your individual choices right up here. The second part that you would like to look at is once you have defined the planet data, which is right up at the top, where we talk about the planet period is about, in this case, it's about 86,400 seconds. And we want to account for albedo as well. In this case, it is about 0.3. And then there are additional parameters that you might be interested to spend some time on. In my case, I'm going to be more interested in positioning or talking about the sun position, where we will talk about the June solstice, or depending on the simulation that you would want to carry out, you can set up for the other positioning parameters. And correspondingly, you have a number that is calculated for the solar flux that's available to you. In terms of orbital parameters, you would see you either can specify the orbit in terms of the minimum altitude, radius, or the maximum altitude, radius. And the best part is you can also look at eccentricity and the periods as options. So moving on, really not spending too much of time here, you can quickly take a look. What ideally we would want to do is we want to start with the planet as Earth, looking at the orbit type as classical, and then we are done with this. So once I have defined this modeling object, this comes and resides here in the simulation navigator. At any given point in time, this is a parametric entity. You could come back and change the essential parameters that you would need. A similar way of engaging on the simulation objects or the modeling objects is defining what we call as the thermo-optical properties. Okay. So there are multiple ways that I can define the thermo-optical properties here. Very quickly bringing to your attention, one such has been created. I can take a quick information here, and this comes in with infrared specific method for emissivity. We are looking at an emissivity of 0.05, absorption coefficient or absorptivity of 0.3, and the index of refraction as 1. So these are the details that are available to you as a part of your modeling objects. These have been done, and the details have been captured very intensely as a part of your modeling efforts, as you would see here. Once your modeling objects are done, I'll quickly walk you through now what we call as the simulation object container, where we are talking about the relationship between the two parts or the two surfaces, edges, or the solids themselves on and how they are connected with each other. For example, the first one, beam to top ring, if I'll give you a quick rundown on how this looks in terms of the relationship. Here, we are doing a thermal coupling for a given set of faces or a given set of edges. And we are going to look at primary and secondary regions or primary and secondary faces. And the last one that you would want to do is, what is that you would want to specify? Are you going to specify the thermal coupling either through total conductance, total resistance, or you have an understanding of the heat transfer coefficient that's available to you, or there is an edge contact definition that you would like to define? In this case, we have done a edge contact, which is around 35 watt per meter Kelvin for a particular length, in this case, meter length. Once you are done with this, you can go back and take a quick look. Where does this reside? It's right up here. And similarly, you could add some more simulation objects. For example, you would want to look for the radiation requests. Okay. So what are the entities for which you would want to have the radiation requests, whether it is for the top external radiation, or is this the non-dominant or say non-top elements for the radiation requests? So that's something that you will be able to articulate. We are still in the process of setting up our model here for the simulation. And what we are looking at is, we looked at the modeling objects where we defined the orbit. And also we talked about the advanced thermo optical properties like emissivity and absorption. The next one that we quickly did was we looked at the simulation objects where we talked about the thermal coupling. It can be a very intense and advanced thermal coupling, or we can look at straight out of the box, or should we say the automated thermal couplings. And then we looked at a very quick understanding of what we can do with the radiation request. And then finally, we are going to take a very sneak peek into the constraints and the loads. Okay. So let me come to the loads first. Now, what are the loads that we are talking about here? We are going to talk about a quick set of 220-watt load. That's the heat load that we are seeing from these elements. Okay. Now, this could be a linear load, heat load, or it could be driven through a couple of expressions or parameters. For example, it could be measured, or it could be an expression, or it could be a function, and it can come from different unit forms. Okay, so SimCenter Space System Thermal is unit independent. Anything that you punch in will get carried and baselined with SI systems and can be retrieved in the form and the shape of the different unit systems that you will need, the outputs. So we have a component of 220 heat load. Then if I look at the four thermal solar panel thermal loads, I see a heat dissipation of 150 watts. And this is happening. The selections are based on elements, or it can be, if you are doing it for the duct, it can be duct fluid nodes. Okay. So what we have here is a series of a load container, which essentially talks about all the load bearings that is going to happen onto this particular model for this simulation. Once done, we have set up a simulation here. The way you are going to do it is either you jump start with doing a space system thermal, what I have created one here, or it's as simple as we are going to go ahead and say, quickly. So either I can do it from the bottom end, or I can just go ahead and say, I would like to create a new solution. And in this case, we are trying to drive a space system thermal conversation. And what are we trying to do? Are we trying to do a thermal simulation, or are we trying to superimpose or map the thermal simulation results to the structure? Okay, so you have hybrid workflows that are available to you. In this case, we want to do thermal for the space systems. Okay, so that gets created here, and you have these loads as well as the boundary conditions, including the constraint sets defined. And once you hit a solve, you will see a series of results. Okay. In the interest of time, I'll quickly walk you through the results. The results are available here to me once the solution is done. And if I do a double click, you will see that, okay, the simulation navigator intuitively changes to the post-process navigator. So the software is intelligent enough to understand that now you are moving from the simulation to the post-processing engagement, hence provides you a series of tools and the workflows where you can navigate the results. For example, we are looking at the thermal simulation here, where we wanted to understand the absorbed radiation as well as say the incident radiation flux, for the planet and the albedo details and the sun. While this can be one, just to give you a perspective of how this looks like on your screen, you could also specify in a single window multiple entities. The way I would like to do is very quickly, while I am able to see the radiative flux for the planet and the element, we would like to see the absorbed the radiative flux for the albedo. For instance, you would want to compare. So here is the example that you could do a side-by-side comparison or say side-by-side play. On the left-hand side, you have radiative flux, and on the right-hand side, you have absorbed the flux for albedo details. Okay. Now, once you want to come back, you can quickly go back to the model and say set it up for a single view. In my case, we would want to understand a little more in terms of what are the maximum temperatures. For instance, here, where we are going to look at the temperature distribution. And you would notice that here we have on the left-hand side of your view, the finite element model. And down to the right-hand side, you have the results. Okay. What can you also do is you can animate, or you can go and play around with the results a little bit. For example, if I want to animate the results, I can quickly go ahead and say, do a quick animation, look at how the temperature distribution takes place for a given set of boundary conditions that we have established, which ranges from minus 55 degrees all the way up to 85 degrees. I'll take a pause here. And what I would like to do is I would like to go back to my single view. And then we would like to plot the temperature variation. Or if I want to iterate my simulation with the timestamps, I can pick one of these increments, for example, increment 55, and then we would like to see how the temperature distribution happens. Again, very quick, intuitive interface, helping me to articulate the start iteration from 32, end iteration 58, and then I'll just go ahead and say, see how the temperature distribution is happening across the satellite. What's more interesting is I can very efficiently do a quick probe where I can come back and identify the results. For example, these could be your sensors, or these could be your virtual measures where you are identifying the details, and you can output them to a given Excel sheet or notepad. You can copy the information and so on. That's all we wanted to see on a hands-on session live on SimCenter 3D Space Systems Thermal. And as I did mention to you, it's a unified interface, which essentially helps you to navigate various aspects of your thermal modeling, including the pre-processing, solution, post-processing, and of course, associating your model with the geometry. That's a integrated design and the simulation concept. What we will do is we will go back to the contents that we started to share with. Okay, so we talked a bit more in detail about the leveraging the CAD, primarily helping you to be in sync with the design team if there is a design team separately doing these entities. Otherwise, if you are a project engineer, which it happens to be in the case in the Indian ecosystem, most of it, I do see that, okay, the designer will also don the role of the simulation engineer and vice versa. Okay. So this helps you a great benefit in terms of reducing your overall preparation time, and also keep the geometry and simulation integrity and the feedback real time. So with that, let's move on to the next one, where we are going to spend some time understanding. While this was a very simple example of putting up our satellite in the orbit, asking for the orbital loading in terms of the radiative heat transfer and what happens inside the satellite because of the radiative heat transfer and the conductance. We will use some complex, or should I say some advanced simulation methods, which will help you to reassess or recalibrate the physics that you are simulating, and helps you to model the virtual model a lot more closer to the actual physics that is happening in the space. So for that, what we will do is we'll take another example of the SJF assembly. In this case, we have created multiple solve sets. As you would see on the left side of your screen, we have orbital heating requests that are already triggered, and these are for the various type of the elements. As I did mention to you, either you can pick the whole geometry of the satellite, or you can go back and pick a series of surfaces embedded with the top elements that can be picked. Here, what you're doing is you are trying to establish the orbit and the positioning of this satellite in the context of orbit. And the beauty with space systems thermal is you will be able to see how the satellite is being positioned with respect to the planet and how it is going to orbit. For example, in this case, the satellite is orbiting the Earth, and we have defined certain parameters. So this helps the infographic or the visual representation helps you in positioning the satellite a lot more smoother and a lot more quicker. The Orbit Visualizer is an embedded tool or an embedded workflow function, inside Space Systems Thermal, helps you to navigate through the visual aspects. The two simulations that we want to do, one is the orbital heating, and after that, we also want to take a look at how the cooling affects the payloads. In this example, what we are seeing is these are the payload panels. If you remember, we explored this as a part of our earlier example, the MCU, PDU, and the payload. What we are doing right now here is we are assigning certain heat generation entities to these payload elements. And how are they connected to the atmosphere in terms of discharging the heat, either through what we call as the uh, evaporation radiation mechanism, or the condensation condensation and radiation mechanism. So here we are doing the thermal coupling either through a total conductance method, which can drive the conductance through a static value, or you could specify the total conductance through a conditional builder. Basically, you're building a function or an equation which will determine the conductance. So a very classical example of incorporating your what if scenarios. In this case, we are going to settle down for a constant value. So we are just going to knock it down and say this is about 20 watts per degree centigrade. That's about it. So once you are done with the thermal coupling, we will reload our the payload assembly here. And this is a very critical area that we wanted to highlight, where we are going to look at the 1D connections, or basically the piping modeling that we do. This is a very hot topic in the industry today, where we are going to look at the pipe modeling and the effect of heat pipes. There are four pipes that you see. So there are four pipes that you see on your screen. And in terms of thermal coupling, what we are doing is we are associating these pipes to the payloads, okay, through the different mechanisms or through the different methods. One of the things that we would like to do is showcase the piping cross sections so that you get a visual representation, or you can keep them in terms of the bare minimum entities on the assembly side, what you will see on the screen. So similarly, for the heat pipe modeling, you can also use what we call as a HTML page, which I'll come to in a minute, where you can specify an additional details, for example, equivalent heat transfer coefficients, or you can do condensation and evaporation inputs, depending on what input you have, whether it is total conductance, evaporation, or conductance availability, you will be able to model it. In our case, it is going to be equivalent heat, and that's about 2500, what you're seeing on your screen. And a similar thing has been done for the four heat pipes that you look for. So once we are set up with the simulation file, we'll go ahead and say quickly solve this. In the interest of time, we already have done this solution. And if you look at the various elements of PCU, MCU, we are basically looking at the maximum and the minimum temperature distributions, primarily with the cooling or the heating pipes and the conditions that we are looking at. And the side-by-side comparison of having orbital heating for load case 1, and obviously orbital heating for load case 2, that's hot transient 2 results, will really give you a seamless, comparison on what are the changes that you induced into your boundary conditions or into your design, and how they are impacting your changes in the overall results. Okay. You could also create a series of snapshots or templates, which can be proprietary to your organization. For instance, a specific set of uh, a template formats that you should be able to generate using SimCenter Space System Server. What we are seeing right now here is a Java file, which we will open up and take a quick look at how we are going to see the heat pipe and how the temperature distributions are over a period of time. For example, I can pick up heat pipe 1 and see what is the temperature distribution in terms of seconds versus degree centigrade, and how this is getting really translated. Okay. You can pick and choose the details on the area or the region of interest that you would want to do. Similarly, you can look at the heat pipe 2, 3, and 4. And if you look at the BC data input file, which is obviously, as you will see on the screen, it gives you a lot more details in terms of various temperatures for evaporation, condensation, and so on. And you will be able to pinpoint and articulate what are the temperatures that you will be looking for your downstream simulation activities. So that we conclude what we call as using the advanced simulation methods, especially simulating the heat pipes, which are very much in need, and it's a very popular trend these days to take a look at in articulating your radiative, conductive, and convective heat transfers in the space industry. We touched upon this very briefly at the beginning, where we talked about parameterizing the models, because you run through so many operations, whether it is hot condition, cold conditions, or inertial conditions, or what we call as the static conditions. And these are the entities which are created. For example, these are the parameters which are needed to create multiple combinations for different modes, whether it is safe mode, operating hot mode, operating cold mode, standby, and so on. So how are we going to do this is using, again, a very uh, seamless integration of the parameterization entities into Space System Server. Let's take a very quick look at this. You have seen the SJF model. What we want to do now is pick one or two. For example, these are the 6 or 7 iterations or the combinations that we have for the MCU and PDU loads. Okay. Now, you can go ahead and say define the parameters for the thermal loads, and these thermal loads can come in from expressions, and those expressions are driven either by an Excel sheet or by the manual inputs that one would do. In here, we are going to see the expressions which are named, where we are going to talk about albedo. For instance, it is 0.55, slightly on the higher side, as against 0.3 that we specified earlier. So these gives you, some initial ideas, or say the initial references. And rest of the angles are derived parameters, which basically are referencing to the primary parameter or the variable. In terms of parameter tables, you can either import a parameter table or you can create one, what you are seeing on your screen. And once you have a parameter series, you will be able to articulate, or should I say, you will be able to create a custom ribbon bar for the parameters, making it your own, so that you can access it very quickly without really spending too much of your time onto the other elements. So what we do is we want to add expressions, and these are the expressions that are available to us in the part. So we'll pick up the first 6 or 7 and we'll add it to the table in terms of the parameters. And this is a configuration one, and you can either activate it or you would want to duplicate it, change the values so that it becomes parametric. And of course, it's a series entity. Okay. You would do the same thing for operating hot, operating cold, static hot, static cold, and so on. The other way is you are going to drive this parameters through an input file, what you're seeing on your screen. You could always use one of the best practices always with the software is to remember the path of the file that we are choosing. Okay. This eliminates when you move the file, either the source file or the simulation file, helps you to really keep it in track. So the parameters are bidirectional in terms of associativity. Either you can edit them inside the SimCenter Space Systems thermal environment, or vice versa. You can drive this conversation of the parameter tables through an Excel sheet. As we just saw, we edited one of the parameters as 0.5 that gets updated or that gets reflected in your parameter table here. We would like to keep safe mode cold as the starting point or the active parameter set, and we will get started from there. And once you define these parameter sets, you could really go back and articulate by bringing them in as a part of your simulation, what we are seeing on the screen. So similarly, you can position the boundary conditions depending on the operation, hot, cold, or static, or any other conditions that you would want to simulate. What you will have is a combination of 4 simulations for 4 different conditions, and that's a little cumbersome to manage. And this is where we are bringing in the parameters and the operating objects to make it a little more easier for you in deploying the boundary conditions and get the simulations done. While parameterization of the model is extremely important, and you could appreciate what we saw in the previous slides, it's even more reasonable to talk about how are we going to capture all of this information and automate it. We are talking about AI all these days. We are talking about quite a bit of automation. And here is such an example where we will talk about automating the context in the context of space systems thermal. So for the same SDF assembly, what we want to do is we want to catch hold of the arrangements. That's the stowing as well as the deployed condition. If you're somebody who would want to record a journal, we are doing that here live on the screen. And this is going to be C, C++ or Java source files. And what we want to do is we want to define configurations. I will open up a simulation file and then switch to the modeling or the assembly file here. And as you know, the boom had arrangements. One was the deployed, second one was the stored. Now I want to change the condition from deployed to stored. While the model or the assembly changed, my finite element model remains the same. I go back to the FEM update. The FEM updates because the FEM is created based on the geometry or based on the assembly. Now, all the series of these actions are captured as a part of your journaling, what we call it, or doing our interactive micro recording. So we are going to open this with Notepad, and we will spend some time understanding how this information is captured as a part of your scripting language that has been used. Either it could be NX it could be your Java, C++, and so on. In my case, we are going to change a variable stored to the arguments or to the arrangements. Once done, we will quickly save this, and this becomes a basic reference or a script for us to execute for any given assembly, moving it from the CAD environment to simulation, and this is in a stored condition. The customized ribbon bar gives you the provision to create a brand new talk or the UI on your existing UI, and then you should be able to put in multiple commands. What you are seeing on your screen now is you are able to create a new user-defined command with the prescription of the previous journal, what we had written, the source file for the arrangements. And in this case, the condition is stored or is it deployed, okay? Or it can be from deployed to stored and vice versa, depending on the context and the configuration that you would want. You can associate a image to this, making sure the team understands the feature functions that are necessarily needed for this one. Okay, once done, you could continue to add few more commands to the ribbon bar. In this case, when I execute the deployed, it moves from the store to the deployed condition. Similarly, we can do 3 or 4 configurations and the custom buttons for various conditions like hot and cold cases. You can bring them here as you would see on your screen now. You have cold, operating hot, standby cold, deployed, stored, and so on. We also have a mode called Orbit Beta Suite, which essentially uses all of these methods or some of them to solve the problem for space system summer and the outputs that you're looking for. Remember these operations or the parameter tables that we saw, we created them earlier. They get captured and you have them as a part of your custom ribbon bar, which is very workflow centric to your space system thermal applications. You're going to solve it for the Orbit Beta Suite, which will throw up a series of results. And then potentially you will be in a position to compare your transient simulations for the hot cases, maybe operating 1 and 2. Okay. What you are seeing here is the beta variation from 10 to 45 in terms of the parameters that have been defined. So if we go back to the notepad and see the results, you will be able to articulate the corresponding outputs, whether it is your operating hot, stored hot, or safe modes, and the corresponding 1D or the heating or the piping elements that you wanted to take a look. So with that, we'll move on to, I know we are slightly behind the schedule, but bear with me for another 2 minutes. I think we should be in a very interesting space to talk about. While it's very important for us to understand and appreciate what space systems thermal brings to the table when it comes to the satellite engineering, it's equally important to look at, will the satellite become operational, right, all the way from launch to the orbiting and of course to the deployment. So one of the elements of SimCenter, which is helping this endeavor tremendously, is what we call as SimCenter Motion, where we are going to look at how predicting, analyzing, and of course improving the positions using SimCenter 3D Motion will help you build a robust and real-time feedback giver multi-body kinematics and dynamics profile. On the left-hand side of your screen, you see a Mars rover, which was an improvised version of the earlier Mars rover that was created. Onto the right-hand side, you would see a complete solar panel arrays getting deployed from stored condition to the fully stretched or the fully functional condition. Okay. So what are we looking at? We are looking at the kinematics part of it. We're also trying to see on the right-hand side screen, for example, we're going to look at the flexibility, or what we call as the flex body dynamics, where we are indicating that you can bring in the flexibility of your structures induced either through the structural modeling or through the thermal simulation into the kinematics, and hence re-verifying or revalidating your models not only structurally, thermally, but also kinematically and dynamically. In the interest of time, I'll skip this slide, but most of you are aware, SimCenter 3D Space System thermal has been extensively used in multiple customer scenarios cut across the geographies. Some of the notable ones being back in home here, ISRO uses URSC, for example, uses quite extensively space systems thermal, including SimCenter Kinematics and Dynamics. We have NASA JPL, Jet Propulsion Lab. We have JAXA, and we have ESA, European Space Agency, have been using SimCenter Space Systems thermal, very effectively. In addition to what I just demonstrated today through a couple of AVIs and a small hands-on session, FTD offers space systems thermal customers like you manifold engagements. For example, we are into software sales. We'll also do consulting of your satellites or payload projects that you're executing or you're yet to start as a part of your new product development process. We do services where you might have tight schedules or limited manpower or know-how of some of the aspects that we have discussed today. And we do some deep dive trainings, primarily on the tool as well as say onto the domain. So these are the additional details that I wanted to share with you. Thank you for your time and patient listening. Now I'll hand it back to Jeevan for questions and any feedbacks that we have either through chats, or you are more than welcome to open up your muted mics and ask questions. I don't see it, but yeah, I see a hand being raised. So either you can type the question, sir, or I think
Okay,
it's Mr.
so am I
Pratik.
audible?
You can go
Yeah,
ahead and ask your question, sir.
yeah. Am I audible? Hello, hello.
Pratik, hi, you are audible.
Yeah, yeah. Okay. Hi, hi. So yeah, my name is Pratik, and I'm currently working as a thermal engineer at Pixel Space. Uh, I, I, yeah. So I have a question. I have a I think there is some echo. Okay. Now it's fine.
Yep, it's okay.
Okay.
Can you speak a little
Uh,
louder, sir? That's okay.
yeah, yeah, yeah. Just checking if my voice is good, if I'm audible now.
Yeah, you are audible, sir. Please go ahead.
Okay. Yeah, yeah. So I wanted to understand whatever parameterization automation you showed, is it available in the current? I mean, do we need to buy any separate heats or MDA license for this particular analysis? Is it like extra license we need?
Can you repeat the question? I understood the first part.
Yeah. So the automation which you showed, okay, uh, using parameterization technique. I wanted to understand, is there any separate license we need to buy, or it can support in the basic space system thermal license?
there are you don't okay for journaling you don't need interactive
Uh-huh.
lessons and interactive engagement.
Okay.
However, if you wish to completely customize or should I say rewrite the UI, I
Mm-hmm.
think in that case you will need to go and look for some additional licenses of Space Systems Thermal. The toolkit, what we call is the NX Open. Okay. You would have heard of this, but essentially for your applications, what I have shared with you on the screen, you want to do the journaling,
Mm-hmm.
that's available to you out of the box. You just need to be a little more, or your team needs to be a little more sensitive about a few things on the programming. It will
Okay.
be good enough to get.
Okay. Okay. Noted. And you also showed about NX Motion, right? SimCenter Motion. Is it
That's right.
also a separate license, or it can be used in the uh, current space system thermal?
Okay. So still most license, but I can explain to you overall how the licensing configuration works with SimCenter 3D. So you
Mm-hmm.
have a base of SimCenter 3D, and then you have these verticals, whether it is space system thermal or motion or vibrations or kinematics and so on. And
Mm-hmm.
these will consume certain tokens. Okay, so it comes with
Okay.
along with the token system
Mm-hmm.
where you can use a number of tokens for to execute a particular task or an application. For example,
Okay.
space system thermal will consume so many tokens,
Correct. Correct.
vibration will consume so many tokens, and so on. If there is an interest, engage with you to explain to you a bit more on what modules you need and what's the optimum number of tokens that you
Okay. 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 Noted. Noted. Thank you. Thank you for explanation. Yeah.
already.
That- That's what from my side. Thank you.
Thank you. Any more questions? If you have difficulty, you can put your network. We can pick up.